So we'll start something called magnetism. And of course, you can say this as moving charge magnetism. So the story is very old story. So we know that there is a place in somewhere called Magnesia. And there someone found something called the lodestone. And the stone had the attractive power towards certain object, and that some object we call magnetic materials. But at that time, because this happened much before the science was developed in its like a mature stage, it happened a long time back. It happened in maybe some BC. So the idea of, you can say, attraction power of these stones, this is known since ages, but no one was knowing the scientific explanation for the same, why it is happening. The explanation was, the explanation was missing. Then what happened? So after the discovery of atom, you can say people realize that the something fundamental which is governing this power is actually moving charges. Okay. So after the discovery of atom and you can say concept of charge, so we realize that what we realize that these are actually generated because of the moving charge or current. Okay. So moving charge, which we sometimes call current in the context, creates a new field which we call magnetic field. Magnetic field. Okay. So basically, what exactly creates the magnetic field? So the magnetism was something which people thought, okay, it's a very distinct branch of science and it is having different origin. But after learning about the atoms and the charge and all, they realized that okay, the something which is giving a rise to this new property is not exactly uh, you can say a unique thing, but it's a something which we are familiar of. And they realize that it is the moving charge which is kind of facilitating this development of this new field that we are calling magnetic field. And therefore the theory of electricity which got developed earlier and the theory of magnetism, they were like combined into single theory, and then the birth of something, a new theory took place that we called electromagnetism. So now electromagnetism is like a one unique branch, and the electric effect or the magnetic effect are, it's two sides of a coin. It's like a, this gives rise to the both event. So you can say electric or electrostatics field. Let me write down electro static field or the magnetic field, both are actually, you can say, two sides of one thing called electromagnetism, and these are frame dependent quantities. So frame dependent quantities means in one frame you may end up observing the electrostatic behavior. In some unique frame you may end up observing something called magnetic behavior, or in some frame you may be observing both behavior at the same time. But the origin is charge, so it's the charge which is able to create both the effect at the same time. And moving charges are actually capable of creating this new field, and therefore in most of the situation we will come to know that electric field and magnetic fields are always uh, inherently related, and the relation you will study in the chapter of EM waves after studying the Maxwell's equation. Okay.
Okay.
So now it is found that in different inertial frame, in different inertial frame, these two field will vary. The electric and magnetic field will vary. But there was something remarkable that if you add this to magnetic field, if you add by, of course, add in terms of force, if you add the force of the electric and magnetic field on a charged particle, the force remains constant, the effect remains constant, but the total force acting on a charged particle due to electric and magnetic field remains independent, and this combination of force that charge experiences and the sum of electrostatic and magnetic force is, because it was first of all discovered by someone called Lorenz, so it's called Lorenz force. So I think Lorenz discovered that, okay, although the electric and magnetic component varies from one frame to other frame, but the sum of these two forces is an independent quantity and it has nothing to do with the inertial frame. So in every inertial frame, the answer remains same. And because he discovered this particular behavior or property, so we call it Lorentz force. So Lorentz force, which we represent by the symbol FL, is nothing but the sum of electric and magnetic force. So that's how it all is started. Okay. So the Lorentz force is a constant quantity, and if we know about a single charge, let me draw something called lines of force. So if you remember that from electrostatics, we studied that a charge creates the electric field lines in all directions, right?
Yes, sir.
And not only that, it will be spherically symmetrical, right?
Yes, sir.
But what is more fascinating now, I can reveal the fact that the field lines are not symmetrical in every frame.
So in every frame.
Frame means like if you are watching this charge in a frame where it is at rest, it is uniform. But what if you watch the same charge moving? So while it is in motion, the answer will change. So imagine in some frame this is at rest. So you can say, okay, this is the electric field lines, right?
Yes, sir.
So the question is that while in a frame, if you see the charge is in motion, so the field lines will change its orientation or remain same. It is found that the field lines becomes more close to the perpendicular direction. So it is like it will shrink along the motion. So a moving charge definitely will have a different field orientation compared to the charge at rest. But under the condition when V is very, very small than C, if we are moving at a speed which is not comparable anyhow with the speed of light, such discrimination we ignore. Now, definitely in JEE syllabus, we always consider something called non-relativistic effect, which means the motion of charge particle is small enough that all such changes which actually occur at high speed can be ignored, and the laws of electrostatics that we have studied, let's say you know Coulomb's law, which is kq by r square. Technically, Coulomb's law you
Yes.
cannot apply the moment you switch to the relativistic speed. So at that point, you have to have a new way of writing the equation of Coulomb's law. Maybe something very complex, maybe some which involves the velocity. But we keep our syllabus. I mean, because our syllabus is such, we keep all the discussion intact for the non-relativistic condition. So of course, this is this is the relativistic effect. Relativistic. So when you are moving at a speed which is very fast, the distortion will be quite significant. But if it is non-relativistic effect, so what is your relativistic effect? The effect in which the V is, of course, less than, but close to C. And what is non-relativistic effect? When velocity is very small compared to C. So V is okay. Okay. So Lawrence actually introduced something called the some transformation, that the electric field in one frame and the electric field in the other frame they will not look same, and there is a transformation rule that we call Lorenz transformation. And if you ask me what is Lorenz transformation, I will say it is the dependence of value of electric and magnetic field with respect to frame of reference. So it is the transformation of E or B under various inertial frame of reference. Okay. So it is a transformation of E or B under various frame of reference. Okay. I'll just show you some of the transformation formula just for the purpose of writing. Okay. That how this transformation formula looks like. Okay. So again, the Lorentz force, we know we can write as Fe plus Fm. So to get the glimpse of how it is done, the electric force we know that we can write as a charge particle Q into E, right?
Yes.
And you will also study in magnetism that the force on a charge particle we can write as Q into V cross B, right?
Yes, sir.
So if I just simply take the charge common, then this we can write as E plus V cross B. Okay. What we can write?
SB cross B.
And if I call this the net force as some sort of extended electric field, the transformed field, let's say this is the new electric field. Let's say I'm forcing myself to express the answer in terms of electric force. So this you can say forced electric field, and that must be equal to how much? So now, okay, let's try to understand what I'm trying to do here. Imagine if a charge particle is moving, then the electric field will apply this much force, and a moving charge experiences this much force, as we know from the some formula in magnetism. Let's say you know this. Okay.
Okay, sir.
Now imagine suddenly a charge is moving with velocity v, and you also decide to run. So some observer is also running towards the charge, along the charge with the same velocity. What will happen? For this observer, the charge will appear at rest or in motion.
So at rest.
And if a charge is at rest, then according to him, the force must be absent for the magnetic part. The magnetic force will be 0,
Yes, sir.
isn't it?
Yes, sir.
But the force is experienced by charge, which cannot change, isn't it? Like just because I am running, will it change what you are experiencing?
No, sir.
So in order to manage or maintain the same status quo about the force, can we say the electric force, because it is now at rest, so can we say the only force that this charge is experiencing is electric force?
Yes, sir.
But this electric field will be like a transformed field, isn't it?
Yes, sir.
So in a way, this is what I'm trying to explain, that the electric field now is a transformed one, not the original one, because the net force cannot change. Na?
Yes, sir.
Just because I am changing the frame of reference, can we say that okay, because I have changed the frame of reference, then you should change the force what you are experiencing? No,
Yes.
that's not possible, because charge is charge and it must experience what it must experience. Okay, so
Yes, sir.
that therefore we can say that definitely the change of reference must be changing these fields in a way which is which in turn maintaining the net force, right?
Yes, sir.
So the net force should not change, and that's why now we introduce an electric field formula when the observer is moving with velocity v. So now this is a way of saying that. So the moment you move, and let's say if there is a space in which the electric field is pre-existing E and magnetic field which is pre-existing as B, and if this is the E and B is observed by some another observer which is at rest, then a moving observer will experience this electric field. Understood? A moving
Yes,
will
sir.
experience a new value. But Lorenz said that, okay, this is not the right way of writing. He said, okay, you have to also apply the relativistic effect. And then he introduced a constant gamma, which you can multiply. And later on, the gamma came from the theory of relativity. It is written as 1 upon 1 minus v square by c square under. Now, for relativistic effect, gamma is pretty much a dominant quantity. Like it's something which can change the answer significantly. But for non-relativistic effect, this term will be always equals to 1.
Yes, sir.
So we can say that for non-relativistic effect, so roughly equals to 1. And therefore, what we wrote earlier was correct, right?
Yes, sir.
So this is called Lorenz transformation. This is called Lorenz
Transfer.
transformation. And the V represents the velocity of frame. So V represents the velocity of frame. Okay. But he similarly introduced something called the transformation of magnetic field as well. So even the magnetic field won't be same. Understood?
Yes, sir.
So the magnetic field will also change under such scenario. And there is a way of writing. Okay, so we'll see how we can write the magnetic field when such change will take place. Okay.
Sir, like forced like B dash.
Yeah, right. So
Okay.
B will also change and it will become B dash. So the moment you change the frame of reference, the B has to change and it will give you a new value B. So
Yes.
the way we are writing B is interesting, and that will be the basis of solving the problem. Okay.
Okay, sir.
So the magnetic field, and of course that is B vector, and we assume that the electric field that we so
Sir, can you just come back in a minute?
yeah, sure. Okay, you're there.
So,
Hello, you're there.
yes, sir.
So what I said is just like the electric field varies, if you go from one frame to another frame, let's say if this guy is looking at the point and at this point the field is B, if this guy will look at the same point, will he say B or something different? So the answer is he will see something different, not B. Understood?
So your voice is cracking.
Okay, am I audible now? Hello, hello, 1 2 3 1 2 3. Can
Yes,
you
sir. Now you are.
re-log in? I think
Yes, sir.
just do it once.
Okay, sir. So able to hear me?
Yeah, I can hear. Can you hear me?
Yes, sir.
Okay. So similar to the shift of the value of E observed by the inertial frame which is in motion, we can expect a similar change in the magnetic field, right?
Yes, sir.
And this value of magnetic field we write as the B original minus V cross E original upon C square. And of course, you can multiply with gamma to make it exact. But under the non-relativistic assumption, this all thing will be gamma we can treat as 1, right? As we discussed. Why?
Yes, sir.
Now, to understand how to apply this formula exactly, we need to know something more. And of course, the derivation is beyond the scope of JEE physics. So this is something called relativity, in which we derive from scratch only at a very high advanced level, let's say master's level, not at even a graduation level. So imagine the coordinate system, and there are certain rules that we need to know. So the rule is that, let's say, the electric field or the magnetic field should be perpendicular to the velocity of frame. So if the frame is moving, let's say we have a frame S which is at rest, and there's a frame. I would say the velocity is non-zero, and this is a new frame S dash. And if we choose a point in space at which the electric field is E and B, but these are, you can see the direction of E and B are perpendicular to the velocity, right? So we have taken V direction like this. So V is normal to the plane.
Yes, sir.
So actually we can call this as E perpendicular and B perpendicular. Okay. So the actual transformation is the parallel component will never get affected due to the moving frame. So if the velocity and the electric field is in the same direction, it will never get affected. It remains same. And that is true for the magnetic field also. So any magnetic field which is parallel to the motion of the observer, that will remain unaffected. So only transverse value changes. So this we write as plus the V frame cross like this, and the B perpendicular will be equals to B perpendicular originally present there,
Yes, sir.
and then minus the frame into E, the electric field upon C square. Now, of course, why C square? Because that will make the dimension correct. Okay. So, dimensionally, the C square will come. And of course, to make it in general, you can multiply with gamma. And as I said or discussed that for non-relativistic effect, or I would say non-relativistic speed actually, when V is much less than C, the gamma will be 1, and then you will have the simplified formula. Understood?
Yes, sir.
Okay. Okay. So we can expand by writing this into. So let's say if I say, let's say the velocity of the frame is along x-axis, then what really matters is the y and the z component of electric and magnetic, right?
Yes, sir.
Because if velocity is x, then electric field can have y and z component, but it cannot have the which component? X component. I mean, that will not get affected. So how to write this? You can say E perpendicular dash. We can write E perpendicular as EY JK plus EZK. You can write like this.
Yes, sir.
And velocity is Vx I cap cross. And B we can also write as BYJ and BZK cap like this.
Yes, sir.
I'm not taking gamma because that will only make it complex. So after all this, what we are going to get? EYJ cap. Okay, Vx. What is I cross J? K cap. And what is I cross K?
Minus J.
So I can bring the I together.
Yes, sir.
Sorry, J together and K together. And therefore, I can also write this as E dash perpendicular uh, Y component J cap. Or I can simply say, E dash Y J cap plus E dash Z K cap, just to compare.
Yes, sir.
And if you compare, what we get? The EY dash has become how much? EY minus VX BZ. Okay.
Yes, sir.
And EZ dash has become how much?
EZ plus VXBY.
So let's do it for the magnetic field also. Okay.
Yes, sir.
So the B perpendicular dash, the answer is B dash, sorry, B without dash minus V cross E upon C square. So we can write as B Y J cap B Z K cap minus V X I cap cross EY J cap EZ K cap, right?
Yes, sir.
And Vx Ey, what to get? Vx Ey
Sir, K cap
K cap, and Vx is,
minus J cap.
so I cannot minus here only, right?
Yes, sir.
Upon C square. So let's bring the J component together. So it's By plus and now if you compare, what you can write? Dy dash equals to By plus Vx Ez upon C square, and B dash Z equals to, sorry, Bz minus. So these are the transformation formula that you just need to know a bit about it, not much. Okay.
Yes, sir.
So what I'll do is I'll take one particular case called transverse electromagnetic field. There is something very famous called transverse electromagnetic field. And so in this case, we are assuming that the electric field is along the y-axis. So I'm just taking EY because I'm not taking the EZ component, and B is only BZ. And this is existing in the inertial frame at rest. So if I have a frame which is inertial but moving along Vx, and let's call this frame as S dash, and this is the S frame. So in this frame, if there is any observer, so this guy will only see EY dash, that will be EY. And just to remember, this is V cross B. So you can see the answer. What is EY coming here? EY minus Vx BZ, right? And
Yes,
we
sir.
have also have the EY EZ dash is EZ plus Vx By. But out of these two formula, which one we should use? The first or second? So we are writing EY dash, right?
Yes, sir. So we'll take the first one.
First. So that's why this becomes the minus n, right?
Yes, sir.
So this becomes this minus Vx Bz, right? I think Bz. You can check. It's a Yxz. Okay. And similarly, what is about the Bz dash? Because we don't want By, because we only want Bz dash. Bz minus Vx Ey. Bz dash is Bz minus Vx Ey upon C square. Okay.
Yes.
So just let me confirm Vx Ey upon C square. Yeah, fine. So the formula is simple. The Bz is uh, Bz dash is Bz minus Vx Ey, and so we can always choose a frame in which the electric field can vanish. Let's say if I want to make Ey 0, so what should be the value of Vx so that the Ey becomes 0? Completely remove the electric field, what we can do?
Sir, we equate it to 0 and then EY is equal to VX BZ.
Which means the Ey becomes Vx Bz, which implies something really interesting, that if you have a frame of reference which is moving at a speed which is the equals to a ratio of Ey by Bz. Okay.
Yes, sir.
And if I denote by like this, Ey as E naught and Bz as B naught, this ratio is interesting, E naught by B naught. So if a frame is moving at this speed, then in such frame, the electric field will vanish. Yeah, that's
Yes.
possible. And similarly, for to vanish the magnetic field, it turns out to be same answer. So if you want to just get rid of magnetic field, you have to move a bit faster, right?
Yes, sir.
So you can see it's actually difficult
We have to
to
move
make
too
this
fast.
0. So this becomes, sorry. And this implies B naught C square by E naught. And C itself is a tremendous value. So if let's say B naught is actually very, very small, because we cannot achieve the speed of light, right?
Yes, sir.
So the B naught is going to be very, very small compared to E naught, so that the ratio is always less than C.
Yes, sir.
We cannot achieve the speed of light. And this also gives you condition that what it gives the condition that B naught C square is less than E naught C. So the C must be less than E naught by B naught. Yeah.
Yes, sir.
Or you can say the E naught must be more than C times B naught. Okay.
Yes, sir.
Only for electromagnetic wave, these are equal. Because for electromagnetic wave, the electric field and magnetic field is moving at a speed of light. So the E naught and B naught ratio will be equal to C only. Okay. So the equality will hold true for EM wave. For any particle, this is going to be more than this. So only for electromagnetic electromagnetic wave, you can say the E naught is equal to C B naught. So for EM wave, in which the electric field varies by this formula, and the magnetic field varies by this formula. Let's say this is EY, this is BZ. In this case, the E naught is always equal to CB naught. Understood?
Yes, sir.
But for rest, it is always. So this formula is again very important for you. You can just remember this, that electric field is C times B naught. Magnetic field is very weak field compared to electric. So E naught is equal to C times B naught. Okay.
Okay.
So we'll use some of these formula to arrive at a very interesting answer.
Sir.
Yeah.
Sir, can I just like have dinner now and come back in like
Yeah,
10
exactly. You
minutes?
can also have dinner. I will also have dinner, and we'll come back. Okay.
Okay, sir.
Yeah. So we'll meet after 10 minutes or 12 minutes. Okay.
Yes, sir.
So once you are done, just message me. Okay.
Okay, sir.
Okay. Fine. Okay, so these are some transformation. Of course, these are much beyond the JEE syllabus, but having a basic idea will facilitate some of the learning that we'll see at the end of this chapter. Okay, so
Okay, sir.
there are questions which can be solved by this transformation method effect effectively and easily as against the conventional method. Okay. So we can always, switch the frame and remove the unwanted the field. Let's say if I don't want the EY to be present, I'll just choose a frame, and we have seen the frame must be moving with this velocity to get rid of electric field, right?
Yes, sir.
And if I want to get rid of magnetic field for some reason, I can do the similar thing as we can see here. Okay. So now imagine we would like to know the magnetic field due to a moving charge. So magnetic field, magnetic field due to moving charge. So magnetic field due to moving charge in this case, we'll try to understand something. So let's say we have a charge which is moving, and this charge is moving along this line. So you can choose any direction as you wish. And the velocity of the charge is, let's call V. Okay.
Okay, sir.
And let's call a point P. So this is the point P at which, and we are taking care of the non-relativistic condition, which means the V is going to be much less than speed of light. So the electrostatic behavior is almost intact. It won't change much, okay, as we believe that it will change drastically. So now, if the point P is a point at which I'm interested in understanding something. So first of all, we can say that if this is at a distance r vector away, and if this angle is theta, then at this point P, can we say the electric field will be like this? So that's the electrostatic condition. We know this,
Yes, sir.
and we can write the magnitude of electric field as well, isn't it?
Yes, sir.
So I think we can attach KQ by R square, right?
Yes, sir.
But we know that as the charge will move, what will happen? The field at the
Uh,
point E will change, right?
yes, sir.
So due to motion, the electric field become function of time, right? So in a
Yes.
way, at a given point, if you fix the point and if you start running, the R will change, and as R will change, we are going to witness a different direction and magnitude of electric field, right?
Yes, sir.
So what do we say that a time varying electric field induces magnetic field? What we say?
A
A
time.
time varying electric field induces magnetic field. So we got really interested at what will be its value. Okay. So now I chose a point P, and we can say that at point P, the moving charge will create a time varying electric field So at the same time, we can also expect what is the contribution of, and what exactly is the magnetic field. What I said is it's a frame dependent quantity, right? This is what I said.
Yes, sir.
So imagine, imagine if I create a frame, hopefully this will, yes, yes, sorry. And the frame itself is moving with velocity v. So in this frame, the charge will be at rest.
Yes, sir.
Okay. So in this
Yes, sir.
frame, the charge will be at rest. Okay. Now earlier at this point, we had only electric field, right?
Yes, sir.
We expected that the moving charge will also induce some magnetic field. Now in the frame S dash, we know that the charge is at rest. Okay.
Yes, sir.
And therefore, for this guy, the frame, the point P will create what? Electric field like this.
Yes, sir.
And we know transformation formula from the magnetism that B dash perpendicular was pre-existing B minus velocity of the frame cross electric field upon C square, isn't it?
Yes, sir.
So what we know that this is zero, correct?
Yes, sir.
So in this frame, because this term is zero, can we say that B dash is minus V cross E?
Yes, sir.
Upon C square, isn't it?
Yes, sir.
Because there is no pre-existing field. So in the frame, you can expect some magnetic field at the point P. Okay. You can expect some magnetic field at the point P. And you can see the magnetic field is actually due to electric field only. Na?
Yes, sir.
So magnetic field is due to the electric field. It is not due to something else. It is the electric field which is creating the magnetic field. Understood?
Yes, sir.
Now, how to deal with this minus sign? So there will be a difficulty of minus sign. And what I can do is, I'll give you
Sir,
just, yeah.
E cross V.
Yeah, that is fine. But we have to write V cross E itself. Because that is how we define the answer. So V cross E is coming into the plane, right?
Yes, sir.
Okay, so what I'll do is I'll choose a plus sign. I mean, I can choose something. Let's say it's plus sign. Because anyway, what we need to know is like how formula came to picture. So let's keep it plus. Okay. Now, it will not affect the entire relation anyway. But
Sir,
it will
how
give the,
it won't,
pardon?
sir, I like how it won't affect.
No, if it is if the B existing is there, because this plus minus depends on the way we choose the frame. So what does it mean is actually minus V frame into E. Ah, E is how much? E is there. Ah, I got it. By why it is plus, I will tell you. This is velocity of frame. Okay. So I think in the frame of charge, if you to take the charge as a frame of reference, then the inertial frame at rest will start moving backward. It's like a relative. The V becomes minus V. I mean something like that.
Yes, sir.
If I choose a frame, if the frame is, let's say there is a frame which is at rest, but if you choose this as a frame, the inertial frame will start looking at moving backward.
Yes, sir.
and therefore the minus v will become like minus v cross e. It will become positive, right?
Yes, sir. So in actuality, we are considering the frame's velocity,
Yeah, correct. We are considering the frame velocity.
the frame's relative velocity.
Yeah.
Okay.
So in reality, we consider the frame velocity. So it's a somewhat complex, not very easy. And I mean, of course, it requires rigorous understanding of relativity. And at this point of time, of course, I have understood many times, but because it's not applicable in JEE, I tend to forget, to be honest. Okay.
Okay.
So you can just keep this as a formula. And because the V here, we are writing the velocity of the charge, right?
Yes, sir.
So I think, okay, let me tell you, we are still correct, nothing wrong. The answer is correct, but this is the velocity of frame, correct?
Yes, sir.
And I can say the here the V is representing the velocity of charge, right?
Yes,
So
sir.
I'll just make one more change. Just probably this will clarify everything. So how to express the answer, because the V is the velocity frame. So can we say the frame is going with minus V? The V frame is minus V like this in the like you can say charge frame. In the charge frame, the inertial frame will start going backward, right?
Yes, sir.
And therefore this V frame will become plus V. Now we can replace, right? So velocity of frame we can take as minus velocity of charge.
Yes, sir.
Yeah, so I think we can get the answer like this. And also we can see the direction of the magnetic field at the point P is pretty much straightforward. This is the relation. So what will be the direction of the B at this point P? Into the plane.
Yes, sir.
So at this point the B will be like this. So the direction of B will be into the plane. And because it is into the plane, so it is very much normal to the plane of V and E vector, isn't it?
Yes, sir.
And from Coulomb's law, we know how to write electric field in vector form. So it is Q by 4 pi epsilon naught R square into R cap.
Yes, sir.
And this you can also write as Q by 4 pi epsilon naught R cube into R vector. So we can write like this. Okay.
Yes, sir.
So now because we have a formula, like there's a question 1 and a question 2. So from 1 and 2, what you can say? Can we write the magnetic field? I'm just not writing the perfect. Magnetic field equals to V cross E. So everything constant, we can take it out. Q by 4 pi epsilon naught R cube C square. I'm taking all this common. And then I'm writing the V cross R, right?
Yes, sir.
Now this is the actual answer. So the B turns out to be how much? Q by 4 pi epsilon naught C square into V cross R vector. This is how we derive. Okay. You can see a moving charge is creating a field which we are calling magnetic field, but actually it is indirectly depending on the electric field only. Na? So the
Yes.
magnetic field is not an independent field, it is due to the electric field, right?
Yes, sir.
And it is actually called the relativistic effect of electric field. A time varying electric field induces, or you can say alters its value, and this altered value we manifest as magnetic field. Understood?
Yes, sir.
Now this is interesting, especially for conductors. Now let me make it simplified version. This is a bit complex. The C square we write as under root of 1 upon mu naught into epsilon naught. Sorry. C square is 1 upon mu naught epsilon naught. And this relation is derived from the Maxwell equation. And fortunately, this C matched with the speed of light, which was derived from some experimental, some experimental evidence. And that led to the realization that the C in the Maxwell equation derivation is actually representing a fundamental constant of nature, and that fundamental constant of nature is called speed of light. So speed of light is a finite value. It's a finite quantity. It's not infinite. Because if the C becomes infinite, then B will never exist. Understood?
Yes, sir.
So C is present is the proof that, or you can say C is finite, is actually creating the B. If C becomes infinite, B will never be there.
Yes, sir.
Now, if you substitute, it will take a new form. So this is how we write. So here is the first formula that we derive. So this formula is called Biot-Savart law.
Okay, sir.
So this can be expressed in multiple ways, but now this is the first way of representing. And now you can also realize that why me naught has come into picture. Okay. So although we started with the electric field, now we are eventually transforming into a new formula, and this new formula B is called magnetic field induction. We don't call intensity. So the name is magnetic field induction. And probably the induction word you can say is due to the reason that it is a time varying electric field which is creating this B. So a moving charge is the source of time varying electric field, isn't it?
Yes, sir.
So whenever charge is in motion, what happens? It creates a time varying electric field, and because the time variation of electric field is the root cause behind the birth of magnetism, or you can say magnetic field. Okay.
Okay, sir. So essentially, because it is induced, we are calling it as induction.
Yeah, very much. That's the reason. Hopefully, that should be the reason, but it's not explicitly written anywhere in the text why it is called. Because of some other reason, that magnetic field intensity we define differently in this chapter. So we have magnetic field intensity, and we represent by the symbol capital H. And this is something like an auxiliary field of in magnetism. It's like something similar to the auxiliary field, and it is defined for some reason. So we'll come to that later on when we study about the uh, magnetic properties of material. Okay.
Okay, sir.
So the distinction is very much clear. The B is called induction, H is called intensity. But in electrostatics, we call electric field intensity, right?
Yes, sir.
And okay. Now this is the you can see every independent, even a single point charge is capable of creating magnetic field, isn't it?
Yes, sir.
So a single point charge is capable of creating the magnetic field, and sorry, okay. Now, if you talk about the current carrying wire, okay, what do we mean by current? Flow of charge, right?
Yes, sir.
So if a single charge can create, then definitely we can say any charge present anywhere in the universe, if it is in motion, it must create.
Yes, sir.
And current is nothing but the manifestation of motion of charge, isn't it?
Yes, sir.
So the moment I draw some wire, and of course I'm not drawing the circuit, I'm drawing a part of circuit. Okay.
Okay, sir.
So the moment we have a current carrying wire, and I'm not drawing the entire circuit, and let's say it is carrying the current I. Okay. So if the length of this is dl, let's say dl is the length. Now dl is simply length of the wire segment that I'm taking care here. I light on this side, and it will be better. And the current is flowing is I. Now the dl length is representing basically what? The dl length is representing,
A segment of the wire.
correct. It's a representing segment of a wire. Now we are not actually interested in the current. We are interested in only charge, because
Yes, sir.
what really creates the magnetic field is the charge, right?
Yes, sir.
Okay. And because uh, because this creates the, because it is nothing but the flow of charge, so the dl is the length of a wire segment, and how we, what we do is we assign a direction to dl based on the flow of current direction taken. And in our case, the I is moving upward. Can we take dl vector in that sense only? So when you
Yes, sir.
take the dl element and then we write I dl as a vector, this is called current element.
Yes, sir.
So current element is called IDL, where the DL gets the direction or its sense, you can say, using I. Okay.
Yes, sir.
Now, if you zoom inside this segment, you will see a lot of many charges present there, right?
Yes, sir.
And if all those charges are moving with the velocity, which is same as the drift velocity, we have seen that.
Yes, sir.
So if I choose any point P, can we find the magnetic field due to those moving charges?
Yes, sir.
So first of all, we will draw the line which begins from the element taken towards the point P. And this convention will be same as we started with. So we call this as R vector. Okay.
Okay, sir.
So we call this as R vector, isn't it?
Yes, sir.
And now what we do, we write the formula. So I have no idea how much charge is inside, but I know certain things, what I know. So let me draw this, what I understand. Like this.
Sir, just a second, sir.
Yeah.
Sir.
Yeah.
Yes.
So now you can see if you zoom this segment outside, you can see it's like a cylinder, right? And this cylinder will have a lot of charge which is moving with a drift velocity. And if I say N is the charge carrier concentration, charge carrier concentration, then the amount of charge in this elementary length will be how much? The concentration into E, sorry, concentration into
NEAVD.
volume.
Yes,
So
sir.
we can, let's say, A dl into, we can say E.
Yes. Yes, sir.
So we know the charge, we know the velocity. So can we again create the, do the same thing that the, because it's a elementary part, and the point P is will have the contribution from this segment, but it will also have contribution from every other segment, right?
Yes,
So
sir.
can we say this dq charge will contribute only dB value here?
Yes, sir.
Because we are taking a small part of charge. So can we say this will only contribute a small value there?
Yes, sir.
So we write as dB. We don't write a B, we not write dB. Okay. At P. And if you remember the formula, it was mu naught by 4 pi. Q into V cross R
Yes, sir.
upon R cube. I'm just writing, it look nice like this, isn't it?
Yes, sir.
So if you try to derive on an exact fashion, why exactly the way it should be derived? So can we write a dq as mu naught by 4 pi, and the dq we can write as n e a dl, and then vd cross r. Now what we do next is we exchange the place of these two vectors because they have same direction in terms of assumption.
Yes, sir.
So can we write the dBp equals to mu naught by 4 pi and NEAVD, and then I can write the DL cross R.
Yes, sir.
But if you remember the current and electricity chapter, the NEAVD is for what?
Sir,
By
it's the
definition,
current.
that's the current. Now you know we can write as IDL Now, this is the second form of writing Biot-Savart law. And to be very honest, I mean, most of the students, they know this as Biot-Savart. They don't realize that the Biot-Savart law is not having only one form. It can be expressed in multiple ways. And what really matters is the charge. But fortunately, in conductor, we can express the same answer in terms of current. That's like privilege, isn't it?
Yes. Yes, sir.
Let's say if you are not very much interested in deriving this through this complex method, there is a simpler way that you can also choose. So we can write current dq as I dt directly. And if you substitute dq here as I dt, the dt into vd becomes dl, right?
Yes, sir.
So I can write as I, and the dt, if you multiply with velocity, becomes length.
Yes, sir.
So I can say dl is basically not nothing but vd dt. So this is like a simpler derivation, and what I did before was the actual derivation.
Yes, sir.
Okay,
Okay, sir.
but this is not the only way to represent the Biot-Savart law. There is something more interesting. So probably we can see the third way of writing. So dv we got as mu naught by, tell me the format, mu naught by
Sir, mu naught by 4 pi dq into I guess v, sir, should I say vd or v for here? Only
vd.
vd. Okay, sir. vd cross r divided by mod r cube.
Very good. See, if you don't realize, just because you have seen the entire development of this formula, you can easily remember the formula, isn't it?
Yes, sir.
Imagine if I have given you this as a direct formula. You wouldn't have been so much comfortable with the formula. I mean, that's how it
Yes.
happens.
Yes, sir.
So the whole purpose of giving the history and then deriving from the history is this only. You remember the event, you know the how things appear and why they appear, the way they appear, right?
Yes, sir. We can actually feel the formula.
Yeah. So that's why the magnetism is very easy, only because no one is able to make it expressible, it becomes difficult. And now I think if you have remembered the formula, I can guess and I can bet that you will be having really, I mean, biggest comfort with entire chapter. I mean, this chapter is going to be very easy for you.
Yes, sir.
The only difficulty is this formula, nothing else.
Oh, okay,
So
sir.
after this formula, there is nothing which is difficult in this chapter.
Yes, sir.
Okay. All right. So just a minute.
Okay, sir.
Okay. So now we have a simple formula, and it is not like intimidating to you, right? It is now okay. You can absorb this formula, isn't it?
Yes, sir.
So this you can of course write as dv equals to mu naught by 4 pi, and I, then you can add dd dt. So of course, this is I into dl, right?
Yes, sir.
And current we can always write as in terms of current density, like Ja,
Yes, sir.
and therefore the J is a vector, so I can put J here, and I can take A dl together outside.
Yes, sir.
So it becomes J cross R, and A dl becomes volume, right?
Yes, sir.
So elementary volume of conductor carrying current is able to create this much magnetic field, or will contribute this much magnetic field. You can say that way. Okay.
Yes, sir.
So this is the third way of writing the Bayes rule. Okay. AD. Okay. So this is another way of writing the Bayes-Savart law. Okay.
Okay, sir.
Now all the formula we have discussed, but let's come to the direction. Okay, we have realized the direction is V cross E, right? It's very simple. The plane of velocity and the electric field at that point, right?
Yes, sir.
And if you use the right hand thumb rule, you can see the direction is going to be into the plane,
Uh,
right?
yes, sir.
So on the right of the moving charge, the direction of field is into the plane, isn't it?
Yes, sir.
So on the left, can we say it is out of the plane?
Yes, sir.
So any point if you choose on this side, the field will be out of the plane
Out of
for
the
the plane I am taking. Now, I'm not here to talk about that point. I'm interested in something different, and I'll draw once again this diagram.
Okay, sir.
So and again, now I would like to understand the how the magnetic field. Okay, now we know that at that point the field is inside. Now, can you think about locus of all such points which is going to witness a similar change of electric field? The dE by dt will be similar.
Sir, I don't
You-
understand the question.
you know that this charge will create an electric field like this, right?
Yes, sir.
And as it will move, the E will change with time.
Yes, sir.
Now, can you imagine the locus of all such point where the variation of E is going to be similar or symmetrical,
Which the variation?
at which
Sir, along the direction of the charge.
no, you're not getting the point. If okay, how many, let's see, can you think of equivalent point P anywhere else?
Oh, for that it is like or sir, like the same horizontal distance. I mean, like it's just like a ring around it.
Exactly, this is what I'm talking about.
Oh, okay, sir. Sir, so like E will be same where sort of.
Oh, sorry, I just made the wrong place. Yeah, so that's true. Not only point P, anywhere if you move around this ring, which is like a, if you join every point, it will act like a cone, right?
Yes, sir.
And no matter where you choose the point, the electric field will vary in a similar fashion, isn't it?
Yes, sir.
And that is what I wanted you to realize. That's it.
Okay, sir. Sir, varying in a similar fashion means the magnitude will be same.
Yeah, correct. The magnitude will be same at every all of this point. So
Yes,
dE
sir.
by dt will have same value in terms of magnitude, right?
Yes, sir.
Anyway, so because it is V cross E, so the moment you decide the plane of V and E, you know the field is going to be perpendicular to the plane. So at point P, we know the answer is cross into the plane, right? So what we realize that at point P, it is going to be into the plane.
Yes, sir.
So the B direction at this point is into the plane. But if you take this point, then the B will be along the tangent like this. It will look like this.
Yes, sir.
Do you realize this? B is going to be like this.
Yes, sir.
So everywhere, if you choose a point, the B is going to be tangential to that point, right?
Yes, sir.
So from here, you can realize that only when you come to the point in the plane, the field becomes towards you. That's called dot field.
Yes, sir.
And then again further, it is same, right? It's tangential. It will look like this. And I have just drawn single ring, but it is going to be same for any ring which you can draw. And therefore, I can say that the magnetic field is going to be a closed loop. The field lines is going to be like a closed loop, isn't it?
Yes, sir.
So we can say that magnetic field lines will be like a closed loop, and for given situation, it will be concentric circles with center at line of motion. Understood? And this is the line of motion, if you realize.
Yes, sir.
And if it is true for a single charge, then it is going to be true for the current carrying wire also. So if you have a straight conductor, if the wire is going straight, the field lines will always get concentric circles. Okay.
Yes, sir.
If it is very complex, then it will be distorted circle. I mean, you can say a loop, only loop, but not circular. So now what is simple to remember that whenever we create magnetic field lines, it forms closed loop actually. Unlike the electric field lines, and this is the biggest, or you can say the most stark difference between electric field lines and magnetic field lines. In case of electric field lines, what we know, it is like a radially outward or radially inward. It begins from plus and terminates to minus. So there is a certain called something called termination. They terminate. But
Not in the same location.
yeah, so yeah, for they terminate, they begin somewhere, they terminate somewhere. But in case of magnetic field lines, they don't have the beginning or the end.
Yes, sir.
So they are always in a loop. They are not having beginning or the end. So we don't say, or we can't say that it will start from there and will end to there. So that's why the B vector is called pseudo vector slash axial vector. Why? Because there are two types of vector, polar and axial. With origin and axial vector will be without origin. Of course, at every point it will have well-defined direction, and that is tangent to the circle. But that is for that point. But is it everywhere? Is it having finite direction? No. You can see it will change from point to point. Understood?
Yes, sir.
Now, if you look at the formula again, okay, because the B we write as V cross E by C square. So can we say that along the line of motion, the B will be 0?
Yes, sir.
Along the direction of motion, the charge never induces any magnetic field.
Yes, sir.
Okay. The whole idea is, let's say, if you want to understand what is the magnetic field at point P. So the velocity of the charge at this instant can be resolved into two components, V cos theta. Another is V sin theta. Now V cos theta is already along the P. So for
Yes,
the
sir.
component V cos theta, which we can also call the V parallel component, there won't be any magnetic field induction. No. Who will create the magnetic field induction? It is only V sin theta.
Yes, sir.
And because sin theta is coming, then the cross product is obvious that the definition must be in terms of cross product.
Yes, sir.
And this is very much evident. If you take the modulus, it is V cos theta, right?
Yes, sir.
And this you can also remember it's a V perpendicular upon C square into E. That's it. That's the formula. Understood?
Yes, sir.
So the magnetic field is simply the V perpendicular to E upon C square. Okay.
Okay, sir. Yes, sir.
So these are the various ways in which we derive the formula. We need to know few things like how the magnetic field lines behave.
Sir, it should be V sine theta, right?
Ah, my bad. Yeah,
Yes.
it's a. So the V perpendicular upon C. So that's how, like, along the motion we cannot have the magnetic field. Okay,
Yes, sir.
that's not possible. Okay. So in the chapter of force, I'll show you some contradiction that it is quite possible in magnetism that A can apply force on B, but B cannot apply force on A. So they violate the Newton's third law in one way, but they compensate the violation in other way, which we of course don't study at this stage. But I'll show you all those things in the chapter of force when we talk about the force and various things. There I will explain that it is possible to violate the Newton's third law in electrodynamics. In electrodynamics, it is possible to violate. At classical level, we violate, but at quantum level, it compensates. So if you only consider the classical, you can say, approach of classical physics, there is a clear violation. But the violation of classical stage is compensated at some advanced quantum stage. Okay.
Okay, sir.
All those things are there in place, and we will explore as we study more and more. Okay. So
Yes, sir.
today I'll stop here only, because today the idea was to just introduce the concept of magnetic field, how it comes into picture, and how we can go about it. Okay.
Okay, sir.
All right. So I hope you have understood what we discussed
Yes,
today, and I hope you can feel the formula, right?
yes, sir.
Okay. So now see, this is the most difficult part. Now, if you want to read anything in book, you can read very easy. Nothing will be difficult to be very honest.
Okay, sir.
Okay. So see you in the next lecture. Our next lecture is on.
Sir, it's on Thursday, sir.
Fine. So we'll keep on Thursday. Not an issue.
Okay, sir. Thank you, sir.
Bye. Good
Bye,
night.
sir. Good night, sir.